Welcome to the AAVSO webinar series. My name is Bert Pablo, and I am the staff astronomer for the AAVSO. Again, it's great to see all of you here. Today, we're going to hear from our special interest group leaders, but before we dive in, I have a few quick announcements to make, some of which I'm sure you've heard before. We are using the Zoom webinar. At the bottom of the screen, you will see a few buttons. There is the chat box where you've been introducing yourselves. There's the CC or Show Captions button, which allows you to enable or disable Zoom's automatic closed captioning. And also, there's a special button labeled Q&A. If you click on that Q&A button, you will have the option to submit questions for our instructors. You can submit as many questions as you like at any point during the presentation. Don't worry, it won't interrupt the speaker. After the presentation, we'll have, in this case, after each presentation, we'll have a small Q&A, and we will also have a little bit of a longer Q&A at the end once everyone's had a chance to present. We'll try to answer as many of your questions as possible. I would like to sincerely thank our 2025 series sponsor, Boise Astro. They provide online astronomy education, observatory resources, and research experiences to students and schools to perform observations, conduct research, and publish results. Please check out their website at boiseastro.org to learn more about their offerings in astrometry, photometry, and spectroscopy. Support from sponsors like Boise Astro and our donors make the work of the AAVSO possible. To support the AAVSO, please consider a donation by scanning the QR code on your screen or going to aavso.org. All donations are tax deductible and support our mission of enabling anyone, anywhere to participate in scientific discovery through variable star astronomy, now and for generations to come. And finally, I would like to introduce our topic for today, which is SIGs in the spotlight, exoplanets, solar observing, and YSOs. You will hear from the various section leaders for each of these sections, Dennis Conti, Kris Larsen, and Mike Poxom. Even though I made changes to the slide, apparently I did not save those changes correctly, and so they did not show up. It is Larsen with an E. My apologies. You know, you try so hard, and yet sometimes it still ends up not working out. First, you will hear from our Exoplanet section leader. He will tell you, Dennis Conti, sorry. He will tell you all about the section and what they do and how you can get involved. Thank you so much, Dennis. I will stop sharing and I will let you share, and I will let you know when your screen is available. 1 second.
Okay, thank you, Bert.
All right, looks good to me.
Okay, well, welcome everyone. Just a little explanation. You may have heard Bert actually use a couple of terms, special interest groups and sections. We used to call what we now call special interest group sections. So those of you who know it by that name, it's one and the same. So I'll just spend a few minutes talking about the Exoplanet Special Interest Group. Let me first start with talking about who we are. Many of us have been involved in doing imaging with planets and deep sky objects prior to getting involved with exoplanet observing. That was certainly the path that I took. I've been doing exoplanet observing now for about 10 years, which is about when amateur astronomers started to get involved in exoplanet observing. Our special interest group was actually founded 10 years ago in December. And we did that because there was no home at that time for amateur astronomers who were conducting exoplanet observations. So we folded into the AVSO at the time, the exoplanet section. Since then, we've been involved with two major research projects. Initially, we were involved with a Hubble project where professional astronomers were characterizing the atmosphere of some 12 Hubble exoplanets, while at the same time we were observing those same planets from Earth. And more recently, and up to the present, we've been heavily involved in the exoplanet discovery mission called TESS, which is currently ongoing. This is NASA's current discovery mission, TESS standing for Transiting Exoplanet Survey Satellites. And as the name implies, it is doing an all-sky survey of the possible exoplanet candidates. And what we are involved in is helping to confirm those candidates as true exoplanets. I'll say a little bit more about that later. So the SIG itself, what we do is we provide AVSO members with best practices in exoplanet observing. We do it through online courses. For example, we've had probably about over 200 members now who have taken exoplanet courses. The courses have ranged from introductory courses to more advanced courses. We hold quarterly meetups. These are live online sessions to talk about specific topics of interest, either to the members of the SIG or topics that are more timely. And I'll be mentioning one a little bit later in the presentation. We have an observer guide called A Practical Guide to Exoplanet Observing, which consists of best practices in exoplanet observing, as well as a step-by-step guide to using one of the sort of de facto standards for exoplanet observing in the professional and amateur community called AstroImageJ. So it's one guide that provides soup to nuts best practices, as well as a guide through AstroImageJ. We have observing forums. And finally, we have qualification program where we have an agreement with the TESS science team that AVSO members who go through that qualification process become members of the TESS follow-up team. And so far, we've qualified over 30 AVSO members to date. So that's about the SIG. Now, let me say a few words about our observers. What our observers do is to help confirm that an exoplanet exists, and it helps to refine its radius and orbit. And in a little bit, I'll give an example of how we go about doing that. We also help to refine the period and help to also refine the radius of an already confirmed exoplanet. Now, why is that important? Well, if an exoplanet is newly discovered and it's only been observed, let's say a couple of times, the period of the exoplanet may not be that well defined. And the reason it's important that that period be defined is if there are some very precious space resources, for example, the James Webb Space Telescope, they're going to be observing that exoplanet to do, let's say, atmospheric characterization studies. We want to make sure that James Webb is going to be looking at that exoplanet at the time that we think a exoplanet is passing in front of its host star. So getting the period refined, for example, of an already confirmed exoplanet is an important part of what our observers do. We store the results in two places, depending upon the current status of the exoplanet. For those exoplanets that we are involved with on the TESS team, we store them on a NASA database. For confirmed exoplanets, we store them on a database that is managed by ourselves, the AVSO. How do our observers do the observations? Well, what we do is we measure the change in brightness of a target star as an exoplanet passes in front of it. we have some estimated prediction time, so our observers view a target star, measure the flux of the star during the predicted times, and we create a light curve. And once we create a light curve, we use some software, in particular freeware like AstroImage to fit a ideal model, exoplanet model through it. So again, we measure the brightness of the star, we create a light curve, we use software to create a model through that light curve. And from that light curve, which you see here, for example, as the exoplanet passes in front of the star, the little dots in the figure below represent the value of the flux of the star. And you can see this sort of bucket-shaped curve, which is characteristic of a transiting exoplanet. And from this curve, we get a lot of information from the duration of the curve, the depth of the curve, and even the shape of the curve. For example, just even the shape of the curve, we can distinguish whether what we're looking at is a exoplanet or maybe it's an eclipsing binary, which would be considered a false positive, where an eclipsing binary, for example, might have more of a characteristic V-shaped curve as opposed to this bucket-shaped curve. So from, again, just these parameters of the light curve, we're able to determine the radius, as to say the size of the planet, the size of the orbit, and even the inclination from our point of view. That is to say, what is the angle of the orbit from what the observer is looking at. So the important characteristic of the planet that we define in our observations is the radius. Now, one of the important things, of course, what NASA in its mission to look at exoplanets is trying to determine whether the planet is rocky, gaseous, or icy. And that is to say, what is its density? Well, density is a function of both radius and mass. In our observations, we get radius. To get mass, there's a different technique that the professionals use called radial velocity studies to get the mass. So we help provide one part of the equation of density, which is an important part, namely the size of the planet. And therefore, the exoplanet researchers can then get a good handle on what the planet's density is, which is an important piece of information, for example, to see if the planet is rocky and can stably have, for example, liquid water on its surface, which is another part of habitability. So again, the light curve is what we generate and is to our observations. So how have we contributed to science? Well, mostly it's been through helping with the confirmation and discovery of new exoplanets. We've contributed authorship of over 60 discovery papers. Over 30 have been published in referee journals, and one in particular in Nature, which is one of the more prestigious publications. We also have helped weed out hundreds of false positives. I mentioned, for example, the case of eclipsing binaries being one. We also developed the software to help the entire test team, both professionals and amateurs alike, to detect one of the most common false positive situations, which are nearby eclipsing binaries. This is a case, for example, where if we're looking at a star that we think is the host of an exoplanet, and there is, from TESS's point of view, which is, again, the Space Telescope, it sees a dip in light. The problem is that TESS has such a large pixel that a lot of light from surrounding stars gets blended in. If some of that light, for example, is from a nearby eclipsing binary, when the light of that nearby eclipsing binary is merged with the light of the target, it would appear that there's a exoplanet that is transiting. So what we do is from Earth, we are actually able to better resolve the target star and the nearby eclipsing binary, and are able to distinguish then where that dip in light is occurring. This is one of the more common false positives that we contribute to, but because of the potential for many, many stars in the vicinity of the target being potentially such false positives, it was normally done manually to try to look at each of those stars. So what we did, again, was to develop software to automate that process. So not only have we helped with observations of tests, but we've also supported some of the software infrastructure. We also helped develop the initial submission guidelines that observers, again, both professionals and amateurs, would use for submitting their observations to tests. And finally, as I said earlier, we have helped and continuing to help refine the parameters, in particular the period of confirmed exoplanets. I want to say a few words about a new area that we will be jumping into. We have formed a collaboration with our peers in the British Astronomical Association to start looking at transit timing variations to detect planets in existing known systems. Now, what do I mean by that? Well, if you consider that, let's say we've already discovered, for example, an exoplanet transiting a host star, if we see that there is over time a sort of regular change in the period of that planet, that could possibly be indicative of some other body in that system that is causing that perturbation. This perturbation, so-called transit timing variation, can then help with the discovery of another exoplanet in that same system. So this is an area that we'll be working with BAA members. I will be interested in anyone here who has exoplanet experience, who wants to get involved in this project. I'll show you my contact information in a minute. Please get in touch with me. We're just in the very early stages. We're defining currently the process for doing the observations and the analysis, as well as for defining the targets. So again, anybody that's interested in getting involved in that project, if you have exoplanet observing experience, please let me know. Okay, I want to reserve some questions at the end here if there are any. So let me just summarize by saying that if you want to be included on our distribution list, send me an email at dennis@astrodennis.com. And also, as I said, if you want to be involved in this transit timing variation project, also shoot me an email. And also to join the AVSO Exoplanet group, if you go to forums.avso.org, you'll see under group Exoplanet, and go ahead and join and sign up for that. And Bert, with that, let me just leave some time here for any questions. Bert, I think you're muted if you're trying to talk.
You are correct. I undid my camera and I did not undo my microphone. Not my best showing today. Sorry, guys. We have a few questions, one of which is not a question, but just a comment from Gene Malone. And I have to say that I share your sentiments here, Gene. He says, I have to laugh at the term false positive, at finding only an eclipsing binary instead of a mere planet. He says, get your priorities straight. Imagine there's a laughing and winking emoji. As a fellow binary lover, I understand your sentiments. Um, Next up is a question from George Babzeltz. I'm really hoping I got that one right, but odds are I didn't. What kind of equipment is required for an amateur astronomer to contribute to the AAVSO in general? Is there a minimum requirement for a telescope, mount, or camera?
All right. Well, let me take each of them. So, as far as from first of all, it all depends on seeing conditions. First of all, uh, I would say first of all there are a range of exoplanet sizes that are discovered. The easiest, I'll say, are what we call hot Jupiters, which could be detected by a backyard telescope, let's say on the order of, in some cases, 8 inches, 8-inch aperture, ideally larger, 11 inches maybe. We do have some of the new smart telescopes in the 4.5 inch aperture range that are able to detect hot Jupiters, that is to say, where the transit depth is quite large. So it really depends on, first of all, what you're trying to do. If it's simply to detect hot Jupiters, then, in the range of, 4.5 to 8 inches might be possible if seeing conditions are good. It's sort of marginal, but it is possible. As far as cameras are concerned, ideally a monochrome camera. Of course, these days, mostly CMOS cameras. And as far as mounts are concerned, a mount that provides for good tracking. Now, to supplement a modest size mount, doing guiding certainly would be an important thing to do. So I don't know if that generally covered everything, but just to summarize, a modest good mount, a aperture, ideally 8 inches or larger, but certainly 4 inches has been possible. But if you want to do some real science, then certainly 11 inches or larger and a fairly decent sensitive monochrome camera. So hopefully that kind of generally answered it. It is kind of a broad question, but
Yeah. And there are some options if you don't want to buy your own equipment, but that isn't really that isn't really here or there. I know that the Exoplanet watch does have some things where you can check out data if you want to learn how to do it before you buy your own equipment. That's a reasonable option, especially because it's what Dennis mentioned is not a small purchase um, for a lot of people. The next one up, which I think you kind of answered, but maybe more specifically, it says, can the C-Star S50 in equatorial mode be used to detect exoplanets? And I have a feeling the answer is going to be kind of mixed.
yeah, I myself have tried relentlessly. I have a C-Star S50. I've not operated in equatorial mode, but I and others have not really been successful. It's very noisy. As you know, the aperture is very small. So I would say a no on that, to be honest.
Next up, we have Joyce who's asking, have you considered getting in touch with ESA Plato mission, which will launch in 2026 to look for more exoplanet transits? And I believe the answer to that is definitively yes. We've actually talked to someone from the Plato team, although I haven't heard from him in a while. Dennis, do you have any more specific info?
I have made several contacts with them, and quite honestly, I've not gotten a response. But certainly, we would be interested in working with them. The project I sort of alluded to earlier with the British Astronomical Association, part of that is actually going to be contributing to the aerial project. So we will be sort of indirectly, because we'll be using ExoClock as the photometry software and feeding that will automatically get feed into as part of the aerial mission. So we will be sort of indirectly helping aerial, but we would love to work with Plato folks. And I believe, Bert, you have also tried making contact with them. And So yeah, we'd love to hear back from them, but I made a couple of contacts and no response.
Yeah, I had been talking to one person in particular, but it's been honestly, I haven't followed up in a while, so I should probably email him again and just see where things are at.
Right.
Um, the next question is from Lauren, and it's a bit of an unfair question, but I will ask it anyway, and I'll help you out if I can, Dennis. She said, speaking of false positives, I know that test pixels are around 21 arc seconds per pixel, but the point spread function can be much larger. How far away can eclipsing binary be from the target star while still causing a false positive?
Typically 1 arc minute. We tend to actually observe, or I should say, test out to 2.5 arc minutes out to be conservative, but probably more typically 1 arc minute can be sort of blended in with the target star.
Yeah. And it also kind of depends on like what I mean, so for most of these candidates, Tess is going to be looking at things that are somewhat isolated. You know, if you were looking next to like a fifth magnitude star, for instance, it's going to be hundreds of pixels all around it that are going to have a problem. So you're going to have a really rough time dealing with contamination there. But typically speaking, Tess just won't look at those. It'll just
Yeah.
kind of assume that those are a lost cause and move on.
Yeah, I should mention that not only is Tess's pixel 21 arc seconds, but also its photometric aperture is larger obviously than ours. So not only is the pixel size large, but you can imagine the photometric aperture, if it involves, let's say, 3 or 4 pixels, makes it close to 1 arc minute. So you have to consider the fact that the blending is actually on the order of 1 arc minute, possibly.
Next up is a uh, question from Frederick. He says, my question is about uh, the ADU to calculate the, okay, I'm trying to parse this. On a specific star, does the magnitude play a role in the calculation of ADUs? And if yes, does is there a table to calculate the ADU? I'm sorry, I'm having a hard time figuring out exactly what this question means.
Yeah, I'm not quite sure. Of course, ADUs are what your computer would, or I should say your imaging camera would translate the photon counts, the electron counts to. So, and that's of course a function of the magnitude. The brighter the star, the more electrons, therefore the more ADUs. So I'm not quite sure what the
Yeah,
question is.
if I had to guess, the question is getting ADUs into a magnitude. That would be my guess. I'm not 100% sure. But I know that it depends on the gain of your camera as well. But it's a bit of a complicated question to answer. So it might be easier if you send an email about it and
Yeah,
we'll figure
right.
that out a little bit more what you're talking about. Um, says are Luis asks, are standard photometric filters necessary, or will LRGB do?
Okay, so the answer to that question, again, depends on what you're attempting to do. If you're attempting to just do what I'll call casual exoplanet observing, where you're just trying to detect that a transit occurred, then actually no filter or a clear filter would be fine. If you're trying to determine the midpoint of, let's say, an exoplanet transit, then probably a filter, standard filter such as a V filter. Now, an LRGB filter could be used, but when you get into trying to determine the depth of the exoplanet, then the preference would be to use a standard photometric filter such as a Johnson-Cousins or an SDSS filter. So again, it depends on the purpose of your observation, but if you're just casually wanting to detect that a dip in light occurred, then actually a clear or no filter would be fine.
Next up is a question about CCD versus CMOS. He says, I took your class Timothy says, I took your class a few years ago. You said using a monochrome CCD camera um, is typical, but now that sensor manufacturers only want to make CMOS, do you have any recommendations for CMOS? What about recent ones with 16-bit ADC? My other question was about matching dynamic range with the sensor's ADC. I heard you need 2 bits just for read noise and that you really need 14 steps in dynamic range to match a 16-bit camera. Is that true? Okay, that's a very technical question.
Okay, so first of all, you're correct. CMOS cameras are more coming on the scene. In part of my course, for example, I have a whole segment on CMOS cameras. Just to summarize, typically with the CMOS cameras, there needs to be a balance in your choice of, for example, gain to the 3 parameters you'll be varying, of course, with changes in gain would be well depth, read noise, and what we call system gain, number of electrons per ADU. So depending upon the camera, we've, for example, looked at both QHY cameras and ZWO cameras, which seem to be the more common CMOS cameras. And the particular setting of gain, again, is balancing those 3. So if you have a particular camera in mind, if you could shoot me an email and I'll give you what recommendations I've come to hear from folks as far as the settings.
Okay, we'll answer one more question now, and then we will try to get to the rest a little bit later. So the next one says, I am a high school junior and was wondering some ways I can get involved with the AVSO organization. I can take at least part of this. So you're at the right webinar. There are going to be ways to join each of these sections or SIGs if you would like. They have, or many of them have regular meetings that you can attend. There are also some other things. I will probably put up a thing a little bit later with the new website on how to get involved. But if you want any more information than that, feel free to email us and I will make sure to answer your question a bit more thoroughly. All right. Thank you, Dennis. We might get to some more questions later, but for now, let me introduce Kris Larsen, who is the head of our solar section.
Hello?
Yeah, I can see your slides, Kris.
All right.
Feel free to take it away.
All right. I'm here representing the solar people. We have a team of 3 people who make this go. Kim Hay from the team is here as well. And the 3rd member of the team is Rodney Howe. So we're very different from the other special interest groups because we only look at one star and we work during the day. And so you might be asking, why study the sun of all things? Well, first of all, it's the nearest star to us. And of course, it is the star that has the greatest influence on us and the one we know the most about. And there's a lot going on beneath the surface of the sun that we can't see. And so in order to check our models of how the sun works on the inside, we have to look at what we can see, which is the outside. And specifically, we look at what's called the photosphere, the visible surface of the sun. You can't stand on it, and not just because you get burned, because it is gas, it is not solid. And it is literally boiling. It's a phenomenon that we call granulation. Now, many of you have seen total solar eclipses. I hope all of you have. And if you look at a total solar eclipse, you see the 2 outermost layers of the sun, the chromosphere and the corona. If you have a hydrogen alpha filter, you can see the chromosphere anytime you want. But again, here in the solar section, we are specifically looking at the photosphere. So what do we see? Well, what we're really looking for is sunspots, which used to be called maculae. These are dark appearing areas on the photosphere. We also see things called faculae, which are brighter appearing areas. And the faculae are easier to see due to contrast when they're near the edge or limb of the sun. Now, there are many different kinds of activity that the sun has, from flares to coronal mass ejections, but the sunspots are the easiest to see, and that's one reason that's why we count them. And again, sunspots are not dark, they're darker appearing because they're about 1500 degrees Kelvin cooler than the surrounding area. If you could actually surgically remove a sunspot and look at it, it would not be black. It would appear sort of a dull magenta like the dying embers of a campfire. And the great thing about sunspots is that they are transient events. They're always changing. An individual sunspot can last for hours or it can last for weeks, and occasionally they can last for a couple of months. We've been observing these things for hundreds of years. One name that you will often hear associated with early sunspot observations is, of course, Galileo. And one of the things that Galileo noticed was that you could use sunspots to actually measure the rotation of the sun. So sometimes people ask, well, what are sunspots? And sort of a pithy answer would be that they're magnetic storms. It's a place on the surface of the sun where the strength of the magnetic field is somewhere around 10 to 40 times stronger than average. How do we know that? We use the Zeeman effect to look at changes in the spectrum of the photosphere in areas of sunspot activity. Now, I hope that you've heard about the sunspot cycle. Not only do individual sunspots are born, they change, they die, but overall, the number of sunspots on the sun is always changing. It has a cycle of approximately 11 years. It's not clockwork. It can be as short as 7 years from peak to peak or as many as 17. If it was an exact cycle, it'd be a lot easier to predict. Because the sun has these spots, both the darker appearing sunspots and the brighter appearing faculae, the sun is considered a variable star. Now, thankfully, it doesn't vary by a lot. That would be a problem. The brightness of the sun varies by approximately 0.1% over the sunspot cycle. And interestingly, the sun is actually brighter when there are more sunspots at sunspot maximum. And this always freaks people out when I tell them this because they're like, wait a minute, you told me sunspots appear dark, they put out less light, but yet the sun is brighter when there's more of them. That's because people always forget that there are the brighter faculae. And the brighter faculae, taken in total, more than overcompensate for the darkness appearing of the sunspots. So that is why the sun is actually a tiny bit brighter when it is in heavy sunspot activity. Another really cool thing about sunspot activity is that sunspots, like little kids on a field trip, tend to work via the buddy system. They tend to come in what we call bipolar groups. And these individual groups change and evolve over time. And it's really fun to watch an individual group change. Now, what's actually going on here? Why do they appear in pairs? You have to think of the magnetic field lines of the sun popping out of the photosphere like an exit wound, looping around and coming back into the sun sort of as an entrance wound. And this popping in and out of the magnetic field lines actually changes the heat flow in that area of the photosphere. That's why the temperature is different. And when these magnetic field lines come in and go back down, they can actually cross. And when they cross, they actually can interact with each other, snap, reconnect in different configurations, and that releases energy to the outer layers of the sun, which is why the chromosphere and the corona are hotter than the photosphere itself. I'm obviously simplifying just a tad here. And something interesting happens with the sunspots. Remember I said that Galileo found that you could monitor how fast the sun is rotating by looking at the sunspots. It turns out that the sun spins at different speeds at different latitudes. And you can tell this by looking at sunspots at different latitudes. And we call this differential rotation, and it is possible because the sun is made of gas and not solid. And what this does is it twists up the sun's magnetic field in very complicated ways that astronomers are still trying to figure out to this day. But this generates the sunspot cycle. And not only that, every sunspot cycle, the overall polarity of the sun's magnetic field flips, right? I'm not saying the sun flips. The polarity of the sun's magnetic field changes from one solar cycle to another. When I discuss this with my students, I like to use the analogy of a kitten playing with a ball of yarn. If you have a kitten playing with a ball of yarn, you know the yarn gets all tangled and you often cannot untangle it, so you just sort of cut off the tangled bits and throw them away. That's kind of what the sun does with its sunspot cycle. The differential rotation tangles up the magnetic field and it cuts its losses and essentially generates a new magnetic structure. So what happens to these tangled up bits of magnetic field? They get discarded as what we call coronal mass ejections, huge bubbles of gas that are threaded with magnetic field lines. And when these interact with the Earth, we get, depending upon the polarity of the coronal mass ejection related to the polarity of the Earth's magnetic field, sometimes we don't get a whole lot of anything. Sometimes we get a geomagnetic storm. Now you might say, oh, geomagnetic storm, that's when I should go out and look for aurora. Yeah, you'd be right about that, but there's so much more that can be caused than just the pretty lights that we see in the sky. It wreaks havoc on our technology. And this is one main reason why we want to look at the sun and why our AAVSO solar data is important. If we could predict the relative intensity and timing of the solar peaks, we could use that information to plan, for example, when to launch satellites, when not to launch satellites, when would be best times for spacewalking missions for astronauts, when it would be safer, right? Power companies could be on the watch for possible events. But our magic 8-ball is not that great, and the sun is not that constant. For example, down here in the lower right, the red line was what they thought the current solar cycle was going to look like. The purple line was what it looked like through the end of 2024. And you can see that the purple line and the red line don't have a whole lot in common. We are currently past peak, maybe, of the solar cycle on the downward slide. It's a great time to start solar observing. There's still enough sunspots for you to be interested, but it's not during the peak when it gets really crazy trying to identify different groups of sunspots. Because we don't just count the number of sunspots, we count the number of areas of activity. An active area on the photosphere is called a group. Even if it only has a single spot, we count it as a group because it is an area of activity. And areas of activity are more important than individual teeny-weeny spots. So what we do is we count the number of individual spots, and we also identify how many areas of activity those spots are arranged into. And we get something called the Wolf number. Because the number of active regions, the number of groups is more important, we multiply that by 10 times the number of groups, and then add the overall total number of spots. So a weird thing about the Wolf number is it goes from 0, no activity, to 11, one louder, right? Because if you have one spot, it not only counts as a spot, but it also counts as an area of activity, it counts as a group. And we've been using this in solar observing for over 100 years. If this sounds like something that you'd be interested in doing, we'd like you to join us at the solar section. We have our website, the solar interest group. So here is our website where you can find all sorts of information about how to observe the sun safely. We have an observing guide, which is in a number of different languages. And you will learn how to safely observe the sun. Very important, safely. Now, there are two techniques that we recommend for looking at the sun safely. You can either use projection or you can use a filter. And our roughly 70 observers are pretty evenly split between the two. For projection, a lot of people like this because it is safer for your eyes, because you're not actually looking through the telescope. You're projecting the image on a screen. You do not, however, want to concentrate the heat from that image in your telescope. So you don't want to be using your Nagler eyepieces, for example, and you don't want to use this with a catadioptric telescope because, again, the heat can build up inside and damage your telescope. You also want your image to be in the shade so you can see it. So building a simple collar around your telescope is recommended. And you want to keep all of your body parts out of the light path coming out of your telescope. You also want to make your telescope what I call idiot-proof, which means either remove or cover your finder scope because you're not going to need it. For filter, the filter filters ultraviolet, infrared, and visible light. It blocks out like 99.99% of the light and makes it safe to look through. It is safe for both you and your telescope if you do it correctly. Again, remove or cover your finder scope. Make sure that your filter snugly fits over the aperture to prevent the light from entering in the first place. It is not a filter on your eyepiece. It prevents the light from entering the telescope in the first place. And you must check your filter every single time to make sure that it is in good working order. Make sure there's no cracks, no holes, and no other imperfections. You basically hold it up in front of your eye and look towards the sun. And if you could see anything bright through your filter, you don't want to be using it. So how do you find the sun without a finder scope? It's actually pretty easy. You just minimize the shadow of your telescope. Assuming you have a round tube, which most of us do, you just look and see when the shadow of the tube looks round, projected against the wall or the ground. So here is the disclaimer. You are responsible for your own safety, not me, not the SIG, not the AAVSO, and not the manufacturer. So please check your equipment before each and every solar observation. And how do you report your observations? I'm glad you asked. We have our own data upload system, Sun Entry, where you use the same AAVSO username you would use for nighttime observations. And we have pull-down menus for things that you can put in, the month, the seeing conditions. You type in the day, the hour, the minute, the number of groups, the number of spots, and it automatically calculates the wolf number for you. So you don't even have to do any math. And your data is put into the AAVSO solar database where solar scientists from around the world or educators who are just interested in teaching about this can download your data and aggregate it with all the other data that's in there over many decades. And how do you know how you're doing? Well, every month we put out a solar bulletin where we have an article of interest about the sun or solar observing. And we also give thanks to all of our observers. We list them and we list the number of observations that they've done. And this is available for free on the AAVSO website. So, in conclusion, we invite you to come to the dark side. We have cookies. Actually, we're the light side. And here's some cookies. Join us. the few, the proud, the solar team, and here is the email address to get in touch with the solar SIG. So thank you very much for your attention, and I'd be happy to answer some questions.
Thank you so much, Kris. That was a great presentation, as always. Let's go through and see what questions we have. The first one is John asking if we can have a copy of your slide deck, which is all on you.
I don't know how to get it to them, but sure, I guess email me.
Jay says to go to STSO to see lots of solar info, including movies of solar rotation at various wavelengths.
Mhm.
The next one says, is SID monitoring a part of the solar observing section?
Yes, we have only a very few number of SID observers. So we have, to be honest, we've had discussions over the years as to whether or not to continue doing SID observing, the sudden ionospheric disturbances. For the moment, we are still collecting data. But again, we only have a small number of people who are interested in contributing that.
Next is from David. He asks, what size telescope can be used for solar observations? Which filter
Ah,
bands are the best?
okay, here's the good news. You don't need a big telescope. We actually don't want you to use a big telescope. We want to compare apples to apples over decades. And that is the beauty of this data. If we can consistently observe the same way over many years, even though we have different observers, we can statistically put together their observations to look for meaningful patterns in the sun. And so we want you to use a relatively small telescope. A lot of people use anywhere from a 3-inch, 4-inch telescope. If you have a bigger telescope, that's fine. Obviously, the larger your telescope, the more expensive your filter is going to be. If you're doing projection, you don't want a large telescope because you don't want to gather all of that light, right? So you're going to want to stop down the aperture to begin with. So this is a great thing for people with smaller telescopes to do. Now, in terms of filters, there are a number of different kinds of filters. I personally have a Thousand Oaks filter that I love. I've always used them. I've been solar observing since 1989, and I've always exclusively used Thousand Oaks metal on glass filters. There are a number of those Mylar filters that have been used that people swear by. So the big thing is to obviously get your filter from a reputable dealer, and more importantly, to check it every single time you use it. No shortcuts here.
Next up, we have Gregory, who asks, he says, solarham.com gives the daily sunspot number. Isn't this the official sunspot count? And why are amateur sunspot counts necessary? Amateur astronomer sunspot counts necessary.
Because again, part of the, which one were they talking about?
They said solarham.com.
There are a number of different places that put out sunspots numbers. For example, you can get the sunspot number from, I think Big Bear might still do it. SDO does it, right? You can get it from satellites. Well, how long have those instruments been in service for? Not nearly as long as visual observing like Galileo did it. The beauty of the way that we do it is the history and the comparing apples to apples, going back not only decades, but centuries. A couple of years ago, solar scientists took the AEVSO data and other data by other visual observers, for example, out of Belgium, and they were able to scaffold the data together and look at the historical data going all the way back to Galileo and show a consistent history of solar observing and solar activity. That is the value of our data today, that we are still observing in a similar manner to the way people have been observing the sun for centuries. And that is what allows us to compare one solar cycle to another.
Next is just a comment from Jean Malone, who says, excellent presentations, and thank you for doing this so professionally as well as delightfully.
Thank you. It's my job trying to entertain college students for 36 years.
Next up, we say, how do you tell the difference between one big group and two or more smaller groups?
Yeah, that's the fun. That is where experience comes in. I look back, I have all of my logbooks, and I look back to my initial logbooks and I cringe when I look at some of my observations. So essentially what you do is you just practice. You just do the best you can. If you can observe a group evolve from like over a week or over a month, you can sort of tell what's hanging together as one group and what's just two different areas that are nearby. Generally speaking, the sunspots within a group will align more or less parallel to the sun's equator. There's something called Joy's law. It's not exactly parallel, but it's within a few degrees of being parallel. So that's one way that you can do that. Another thing that you can do, and which is how when I first got started, is I would do my observations, do my accounts, and then when the solar bulletin comes out the next month, I would look back and see how my numbers agree with the averages of all the other observers. And if there were differences, I'd go back and look at my logbook and go, oh, I bet I was dividing that into two groups and it really should have been only one. So there's really experience is the best teacher here. And that's why you don't want to get started exactly at solar maximum when everything is incredibly busy. It's actually better to do it sort of now where we're on the downslide. There's still enough to keep you from being bored, but it's pretty obvious where the groups are.
Next up, we have, do you determine the solar number by hemispheres or sunspot positions?
There are two different ways that you can do it. One way is you just put in the total number. You don't divide it into different areas. If you, however, do look at sun entry, you can divide it by hemispheres if you want, if you have that information. If you could tell on your particular observations which is which, we invite you to upload that data as well, but you don't have to.
Next up is a question from Amoli. He says, I've been doing solar observations for some time now, but don't know what else we can do with this data.
Have you uploaded it to the AVSO? That's one thing you can do with it. If you join the solar group today, we are also interested in observations that you've done before. As long as you've been doing them in basically the same manner that we've been doing them, or you can go back to your logbooks and figure out how to translate it over, we'd be more than happy to look at your data and talk about uploading it to our database.
Next up is Girolamo, who says, what about observations in H alpha? Do you have any research programs involving that narrow band?
Nope. Unfortunately, there is no historical precedent for that. So we have no fruit to compare it to. We're really just worried about the apples to apples. And the H alpha stuff is great and amazing and fun and educational and wonderful. It's just not part of what we do. And this is an actual good point to also say, we want you to observe. We don't want you to go on the internet, pull up an image from a satellite and count what you see off of that satellite. We want you, with your instrument, to observe what you see, either projected or through a safe filter on the sun.
Next up, it's a question from Lauren. She says, "Hi, Kris. How
Hey,
sudden
Larsen.
or gradual is the polarity flip of the sun's magnetic field? And how do we identify it when it happens?"
That's part of the fun, because at what depth within the sun are you asking about the polarity flip? At the surface or at the tachocline where it actually occurs within the sun? One of the things that we know is that during the sunspot cycle, what happens is that the sunspots start moving towards the equator. And then you start seeing sunspots not only moving towards the equator, but other sunspots appearing closer to the poles. And the ones that appear closer to the poles have a different polarity than the ones from the old cycle that are moving closer to the equator. So that's one sign. And it can happen at different times in different hemispheres. Not like radically different, but like, months apart. So to borrow that phrase, it's complicated.
All right, we have time for one more question now. Let's see, it's from Roger. He says, "Just acquired an S50 telescope. Aside from sunspot observations, can we acquire granulation images that would be used to gather valuable data acquisition in this particular field?"
I have seen some incredibly beautiful granulation pictures. And again, like the hydrogen alpha, they're gorgeous, they're beautiful, they're educational. They're just not part of what we do. Because we don't have, again, apples to compare that to for a historical record.
All right. Well, thanks, Kris. We'll probably get back to some more questions after everything is done, but for now, we'll move on to Mike. Mike Poxom is the head of our Young Stellar Objects group. This is a very different from the previous two groups. Much different stuff that you'll see. So, Mike, why don't you take it away?
Okay, cheers, Matt. Are you seeing me?
I am seeing you. I do not see your presentation yet, though.
No, I'm actually what I'm seeing is Christine's name on screen.
Ah, yes.
We need the spotlight.
Yes, I can remove the spotlight. There we go.
Ah, there we go. Okay. Just a quick word about kind of how the group started off, really. Basically, I am, and I've always been, a huge romantic. I make no apologies. And the idea of stars being born, it's such a romantic, inspiring idea. It largely came out of a talk I had with a veteran, pardon me, a veteran observer called Mike Simonson, who is alas no longer with us. And this was roughly at the time when the sections were just starting up. And he said, "Oh, I know you're interested in these things, Mike, one Mike to another. Why don't you start up a baby star section? Because that's basically what these are. If you think of it in human terms, a lot of the stars we study are still inside the womb, right? They haven't actually been born yet as stars. That's why they're called young stellar objects, because technically they're not actually stars yet. They haven't started to fuse hydrogen in their cores yet. When they do, they will be bona fide stars. But a lot of things that we're actually looking at are not strictly stars, even though they look like them, which is rather strange. And a very easy way to join the section, but in fact, as far as I know, the only way to join the section is to subscribe to our newsletter. It's a monthly newsletter that I put together myself, sometimes with contributions, which are always welcome, on the general subject of, of very young stars. We have both amateur and professional observers in our books, so to speak. So I just want to kick off, really. Can you all see that? I know it's boring, but as long as you can see it, it's fine. So why do we observe these stars?
It's not showing, Michael.
Yeah, you're not sharing yet, Mike.
I'm not sharing. Okay, wait a minute. Share screen, of course. Ha! How could I forget? Share. There we go. So you should now be able to see it.
Yes, we can see.
Yeah, it looks a mess, I know. So why do we observe these things? Well, obviously they're variable. We are the Associated with Star Observers, so we observe variable stars. They are variable on both different scales and by different amounts. So there's kind of something there for everyone, really, which ties in with the next point. For some of these stars, you don't even need a telescope. One or two, literally one or two, are bright enough for binoculars. And in fact, the brightest of these is a star called AB Aurigny, which is very interesting. It's very intensely followed by professionals, which we'll come to at the end. And we have actually seen it forming planets, because the formation of a planetary system is simply a byproduct of the formation of a star. So there are lots of exoplanets out there, which ties in with Dennis's talk, of course. This is a fairly new kind of field of study, really, because we heard from Kris that observations of the sun go back hundreds of years, all the way to Galileo. Well, in fact, the first, what we might call YSO, which is T Tauri, was discovered in about 1850, but we didn't actually know what it was until 100 years after that. 1946, I think, an astronomer called Joy put forward the theory that T Tauri and stars like it are actually very young stars, and that's what they are. Because it's a fairly new field of study. There is now quite a lot of research being done on it by professional astronomers, and star formation is very useful because it ties in not just with astrophysics, but ordinary physics and biology and also chemistry, because obviously we wouldn't be here were it not for all the silicon and the carbon and all the rest of it that actually went in to that cloud that formed the sun, which also formed us eventually. So it ties in lots and lots of area of science, not just astronomy. And from the point of view of an amateur astronomer, they are virtually all irregular. Now, that means they're interesting and they're exciting because you don't know what they're going to do next. In fact, one of these stars, a star called CQ Tauri,
Just real quick, I can't tell if we're supposed to be seeing something else, but all I see right now is young stellar objects. Why observe them?
Yeah, that's fine. We are coming to that very soon. I actually saw one of these stars vary as I was looking at it. Now that's pretty intense. Some of them vary on that very short time scale. Quite a lot don't, so they can be quite sort of leisurely. So let's have a look. There we are, Bert. These are basically some of the reasons why these young stars vary. Now, we heard earlier.
We're still seeing the same thing, though, Mike. I think maybe you're sharing the wrong window. Because I see causes.html, index.html.
No, you should be seeing this. Wait a minute.
How about you stop sharing and reshare?
Okay. Okay. Let's try again. Yes, I think it's on the wrong window, isn't it? So let's try again. Let's go. Oh, there we go. Yes, it was. It was showing the wrong one. Is that better?
Yes. Now we
Oh,
can see. There we go.
there we go. These things are sent to try us, aren't they? Yes, we did hear from Christine that the sun has sunspots. Well, the sun has sunspots largely as a result of the fact that it rotates. Now, when you get a rotating star, you tend to get a magnetic field. Now, these baby stars rotate very quickly because they are condensing out of a swirling cloud of gas, maybe a couple of times, sometimes even bigger, maybe a couple of times bigger than the solar system. So there's a lot of energy going into forming this star, and as the gas swirls in, it makes the star rotate very quickly. And when you get a quickly rotating star, you get lots of spots. Obviously, when the sun was younger, we think, at least, according to sort of current ideas, that it was more heavily spotted than it is now. But it's in its kind of comfortable middle age, you know, so it's only got a few spots. But this can be one cause of variation in young stars. As the spots move across the star, they cut off some of the star's light, so that makes it fade a little bit. And obviously, as they move off, it gets a little bit brighter. So that's kind of one cause of the variation. Another, as I said earlier, forming stars tend to form planetary systems as well. And as the material that's eventually going to go on and build our planet gathers together, it gets bigger and bigger and bigger. All these tiny grains, they eventually grow into pebbles. The pebbles will eventually grow into rocks. The rocks will eventually grow into planets. So these can be quite large. And if the geometry is right, sometimes it's forming planets, which we call planetesimals, comets, asteroids, all that sort of gunk that you get in stellar systems. They can pass between us and the star, and that makes the star fade. And obviously, as they move away in their orbit, the star recovers again. The star can also interact with its accretion disk. This is the swirling cloud of gas around the star, basically, of which the star is made and of which the planets are going to be made as well. These are very, very violent places. Right? This is not somewhere you'd want to go for a holiday. Very violent, very dangerous. Sometimes parts of the accretion disk can crash down onto the star, and that can give us not dark areas like spots, but it can give us very bright areas. So we get dark bits and we get light bits. Sometimes we can get them both at the same time. And there are other ways in which the star can interact with the accretion disk, which I'm going to see in the next slide. One other thing that needs to be taken into account is when stars are born, they are usually, in fact, some people think exclusively, not born as single stars. So these stars will quite a lot of the time, they will have a companion or companions. And these companion stars can also interact with our forming star. We actually saw this, I saw this happen myself on a star called RW Aurigui, which actually pulled millions of tons of gas off its companion star and just flung it around the system. This made the star fade. And in fact, it's the faintest we've ever seen it. And that happened it's happened a couple of times. It happened in 2015, 2011, and I believe 2018 as well. But this is a very kind of bold idea of what happens to a young star and its environment. This gives you some idea of how complicated it is. There you are. all these things can feed into our star's variability. Some of them can, just happen once, but sometimes we can get lots of these causes all happening to our star at the same time. So we get very complicated light curves. So this is why I want to move on to the next slide, which is just an illustration of, it's a sample of 3 stars that we study. We study lots more. These are just some that I want to kind of pick out. The first one is SU Aurigui. Now, SU Aurigui is one of these stars that you don't need a large telescope for, or normally. If you look in fairly old data about variable stars, you will see its range of brightness is from 9.0 to 9.6. So not very much really as these stars go, but in 2018, it did something we haven't seen it do before. This is actually from a professional paper on this particular object. And these are the variations in different wavelengths. The black one is the interesting one for me because I'm completely a visual observer, just with an ordinary Doxonian telescope. You don't need a driven scope. So, this makes it easier for a lot of people that maybe haven't got a lot of money and can't afford all the bells and whistles. It had a very deep minimum in the visual. Its normal maximum is around about magnitude 9, but in 2018 it plummeted, as you can see here, plummeted very quickly down to magnitude 11. Never been seen before. But this just demonstrates why it's really useful to observe in not just one wavelength. Because if we saw this happening just in the visual, well, yes, it would be interesting. It's actually unprecedented. But by having observations at the same time in other wavelengths, we can actually get some idea as to what's causing this. Because as we go up this graph, basically, the further up we go, the longer wavelengths we have. And here we are in the mid-infrared. And this is interesting because while the star is getting very, very faint in the visual, it's actually increasing a bit in the infrared. Now that tells us, or that suggests, that what is causing this star to fade is having a different effect on the longer wavelength. So probably what's happening is, because the star is obviously surrounded by a cloud of gas, this is the accretion disk, we think what's happening is something happened on SU Aurigui, and because this is an area quite close to the star, the radiation from whatever was happening actually caused the gas here to brighten. But that had the effect at the same time of veiling the star, so it faded in the visual. Again, this is why it's interesting to have all these different filters. The star I want to look at is one of my favourites, the 1117 Hercules. Now, it was actually originally thought to be a long period variable, like Lyra, with a period of about 400 days. Well, that certainly isn't the case. It's a very, very strange object, which is so interesting. I don't actually want to go into it all here. But you can see here, to begin with, yes, it has these very deep dips going down to magnitude 15 or 16 here, probably another one here. And these happen about 400 days apart. But since about 2017, we've seen some much more suddenly and much more frequently, because the star is now starting to show these small dips here that happen once a fortnight. Now, star formation takes millions of years, so you wouldn't normally expect to see such things happening over just sort of literally months. Really, this hasn't been happening previously. This is a sudden phenomenon, and as soon as this starts happening, we get this incredibly deep minimum here. And then we're kind of back to all this chaos up here. Now, we don't actually know what's doing this. It's possible that maybe there's a planet starting to form, but planets don't form this quickly. They don't form that rapidly. So that's probably not happening. So it's anyone's guess why we are now getting these much more getting the deep ones, but getting these second ones as well. So again, one of my favourite stars, V730 CFI. This was originally thought to be a star kind of like the Sun was about 4.5 billion years ago, we call T Tauri stars. As I mentioned earlier, that first one discovered in about 1850. Stars like the Sun were originally this type of T Tauri star, fairly low mass stars. And I've been following this ever since its discovery in 1995, I think. And it's fairly random. I've just got this very, very faint blue line going through here. It's fairly random, not terribly variable, even though we have this incredibly faint minimum here of 15.9. I know that's 15.9 because that's my observation, and it was the faintest this star had ever been seen up until that point. And then we start getting much more variation setting in over time, but there's still not much of a sort of a period there, and this goes on for a little while until round about here we start to get a period forming. Now again, like with the previous star, this is very sudden in astronomical terms. So what is causing all this much more regular variation? And in fact, over the past couple of years, for this particular star, it's been going through a very, very faint period when it's generally between magnitudes 15 and 16. And we think what's caused that is something has happened to the disk. Something has bucked or sort of warped the disk and much fainter. So just to finish, as I said, all this stuff is useful to science. Just a selection of things that the section has been involved in. We were involved for quite a long while with John Percy to look at UX Orionis stars. This is another group of very young stars, and we think they are actively forming planetary systems, and the planets are coming between us and the star, and these stars undergo deep fades. That's basically what UX Orionis star is. Several of them are visible with a fairly small telescope. In fact, UX Orionis itself only gets down to about magnitude 13 at minimum, so a medium-sized scope. The other stars I mentioned here, WW Vulpecula and BO Cephei, are the same sort of magnitude. So you do not need a huge telescope to observe lots of these interesting stars. We've also been cooperating with a Dr. Ilya Potratov, who's at the Institute of Solar Terrestrial Physics. They're obviously interested in other stars as well. As Kris said earlier, by studying the sun, we can study other stars. Well, obviously, possibly the reverse is true, which is why they're interested. And this particular researcher is interested in that star I was just talking about, V730 CPI. And it's him that came up with the idea that it's possibly caused by a warp disk coming between us and the star itself. And finally, we're involved with a project of the Hubble Space Telescope called the Ulysses Project. Sometimes I think these researchers spend more time trying to invent clever acronyms for their project than they actually do on the projects themselves. I can't remember what this stands for, but it's something to do with young stars. This was good because it brought some of our southern hemisphere observers into range, because a lot of the stars that they were looking at, as said here, are in the southern bits of the Milky Way, so they have a much better idea. And this is a very active star-forming part of the galaxy as well. Lots of young stars tend to kind of cluster together in what we call associations, and this is one of them. It's quite close as these things go. It's about 400 light years away, so quite a few of the stars that we studied for the Hubble were reasonably bright. Again, a proof that you don't need a huge telescope. So I'll close there, and if there are any questions, fire them away.
Thank you, Mike, for this presentation. Good as always. We have a few questions and more coming in. So the first one is from Mulugeta. They say, thank you for your presentation. How do jets and outflows in YSOs control the efficiency of star formation? And what are the main mechanisms causing them?
The jets are very interesting because one thing they can do, these are what are called bipolar outflows. They are a byproduct of the way the star actually forms, and because a lot of these stars are physically close together, basically within the same nebula, or actually same region of the nebula. Sometimes what can happen is these outflows are very energetic, and they can actually collide with other nearby parts of the nebula and start off more star formation. We actually call that triggered star formation. And of course, as our newly forming star, the star that starts forming as a result of the bipolar outflow colliding with its little bit of baby nebula, so to speak. Obviously, when that star gets slightly further on in the star formation process, its jet can also do the same thing. And we have actually seen this happening, obviously not in real time, but we can see by the geometry and arrangement of very close sort of very close stars in a particular region how this actually works. So as you move away from the original, if you want to call it trigger star, all right, the stars get younger and younger. So that's basically what's happening. So the outflows are very important. One thing they do is take a certain amount of the actual rotational energy away from our forming star. If they didn't do that, our forming star might actually fracture into a couple of others. And as I said earlier, some people actually think that when stars form, they actually never form as single stars. That's obviously at the moment that's a bit debatable.
Okay. The next question that we have here is from Sauro. He says, congrats for the really excellent explanation. I have a question. Are telescopes with 20 inches of aperture and with a focal range from focal length ranging from 80 inches upwards sufficient? What filters do you recommend for making photometric observations?
Well, in fact, that's actually the same size telescope that I've got. Yeah, it's a half-meter telescope, 20 inches, with a focal length of f4, so that is 80 inches. So that's exactly the same as you're talking about. But you do not necessarily need, a telescope of that size. As I said earlier, AB Aurigae, you can actually see entirely, even when it goes through a fade, is highly visible in an ordinary pair of binoculars. A mid-sized telescope is absolutely fine. You do not, obviously, the bigger the telescope you've got, the more of these stars you can see and follow, but you do not need a huge telescope. Certainly, a 20-inch telescope is absolutely fine. It's what I use myself.
Cool. So, next up, we have, sorry, I lost track of where I was in the questions. Oh, yes. Next up we have, how does resonance enter into the discussion?
It depends what kind of resonance you're talking about. Are you talking about resonance within the star or between the star and the accretion disk? so I'm not really sure. And if I'm being absolutely honest, I'm not sure. I prefer an honest answer rather than try and make one up on the spot.
That is totally fair. Louise asks, do you pair your light curves with spectroscopic observations?
That would be a really useful thing to do. This has often been done at the professional level, but I know Lauren is listening in. Actually, she might be able to tell you more about that. But certainly, a star like AB Aurigui, it spends most time at maximum. It's one of these UX Orionis stars that kind of gets eclipsed by one of its forming planets. So it has the occasional fade. But even when it has a fade, it's only magnitude 8.5. So that's probably coverable by an amateur-sized spectroscope. I wouldn't know, not being a spectroscopist, although it is really.
Okay.
Yeah,
next...
I was just wondering if we had an answer from Lauren there.
Oh, I will bring it up if she responds.
Oh, okay. Yeah, but some of these stars are quite bright. AB Aurigui, obviously. We saw earlier, that's about magnitude 9, as a rule, when it's behaving itself. There's another one skewed as I was looking at it. That goes between about magnitude 9.5 and about 12. It doesn't usually get down to 12, so it's it's reasonably bright as a rule. So there are several of these which can probably be studied by amateur spectroscopes, but certainly one of the things that we provide are the light curves, so the professionals can then coordinate what's happening visually with what's happening at the star, which we can't do, obviously, as visual observers.
All right, I will do one more question for Mike, and then we'll start weaving some in and out until we have to pack it up. So Arpita says, thanks for the amazing presentation. I am 14 from India and deeply interested in this topic. I want to contribute in the future. Okay, so that's not really a question, but I would suggest you sign up for the newsletter and learn more that way.
Yes, I mean, that is actually how you become a default member of the section. You sign up for the newsletter. That's it. And to do that, you simply send me an email, which I'm sure someone will provide. Newsletter mailing list, and you are then a member of the section or special interest group.
Okay, so going back up to the top here, this question is for Kris. It is, why do sunspots occur?
Well, as was mentioned also in Michael's presentation, magnetic field of the sun gets twisted around. The sunspot, the magnetic field lines pop up, whip around, go back in. And at that exit wound and entrance wound, that moving of the magnetic field line through the gas constricts the motion of heat, and that reduces the temperature, which is what causes that darker appearing nature. So if the sun wasn't so complicated in the inside, if its magnetic field wasn't so complicated, if different layers didn't rotate at different speeds, then it wouldn't have sunspots, but it does all those things. So it has spots.
This one is not so much a question, but it was something for Dennis to comment on. Gary Shaw mentioned that the Pandora mission is going up pretty soon, and that there are some ways to contribute through that with respect to exoplanets. I don't know if you know anything more about Pandora, Dennis, or if you wanted to speak on it. I don't know.
It's going up, I think, the fall of this year. I think the purpose is to look at 20 exoplanets to characterize their atmosphere. It's going to be looking in multiple wavelengths, both visible and infrared. And so the purpose is, again, to look at in the infrared, any atmospheric extinction, to look at characteristics in the atmosphere of those exoplanets. So I think the contribution of amateurs, these are confirmed exoplanets, would be to just help, again, refine the period so that it's looking at the targets at the right time. And as was mentioned, Exoplanet Watch program, NASA's Exoplanet Watch program, will be focusing on that mission. And so anybody who wants to contribute can certainly go to Exoplanet Watch, and those observations most likely also will be entered into our database.
Okay. The next one is a question for Mike. Do you have any recommendations on finding interesting targets outside of the YSO SIG program stars? Determining what makes a good target? Any recommended reading or projects to follow?
Oh, funny you should mention project, because something I didn't actually mention of the things that we do. We are currently actually in the middle of a project of a star called TV Crateris. This is a particularly interesting system. It's a double-double. It's a system of 4 stars, which are arranged in in 2 sets of 2, and one of these sets of 2 about to pass in front of the other, and the set of 2 that's going to pass in front has an accretion disk around it, whereas the other one doesn't. Those stars are slightly older. They're actually now proper stars. They're not baby stars, and that is, it may be starting to happen actually now. In the sense of now as we speak, not sort of a couple of months' time, actually starting to happen now. So that's something that we're doing at the moment. We already have some observations. What's really happening currently is that we are seeing the sort of spotted star phenomenon. We're seeing very, very sort of gradual, not very large ranges of change. As a concern with the stars that you ought to be looking at, say there is a list which is available. Something that we're now starting to see are stars that look like young stellar objects where you wouldn't expect to actually find them. This star that I was talking about earlier, V1117 Hercules, because stars form from these, large clouds of gas and dust, which are found along the plane of the Milky Way. V1117 Hercules is about 800 light years, I think, above the plane of the Milky Way, where there is no star-forming material. So what is it doing there as a young star? Is it in fact a young star at all? It's certainly behaving like one. We've found another one, BP Piscium. It's in Pisces. Obviously, it's a long way from the Milky Way, doing kind of the same thing. And the star I just talked about, TV Crateris, that's a long way from the Milky Way as well. But they're all young stars where young stars shouldn't be. So those particular ones are interesting. But generally, the thing to do is base your program on your equipment. So if you've only got a small telescope, you want to observe stars like AB Aurigae, CQ Tauri, and so on, which are reasonably bright. If you've got a scope the size that we were just talking about, same as mine, at 20-inch, I can, for instance, look at those very, very faint minima of that star V730 Cephei, which I've seen at about magnitude 16.5, something like that. But really, base the stars that you look at on the equipment that you've got. Obviously, if obviously if you can observe in more than one filter, that's even better. One of our most active observers uses a CMOS camera. So there's kind of something there for everyone, really.
Awesome. I think we have time for one more question, and then I'll move to wrap up. Looks like Lauren. Lauren, he says, "Hi, Mike. How often are new YSOs discovered within the reach of amateur observers? Would you say that the YSO sky has been thoroughly mapped, or does their unpredictable behavior mean that new ones keep popping up?"
Right. Well, I think the bright YSO sky has generally been discovered. It's fatal, isn't it, to say something like that? But I'm going to say it anyway. That's why I mentioned earlier these stars that are YSOs where YSOs shouldn't be. These are now the things that are going to start to come to the fore. How you find them is a bit more difficult, because obviously there are millions of stars out there that are a long way from the Milky Way, and we can't look at all of them. Generally, the way these stars are discovered is by sort of mistyping. For instance, one of the stars I was talking about earlier, Bo Cephei, that was originally thought to be an eclipsing binary. It's an Algol type star. The 1117 Hercules was originally thought to be a long period variable. So it's worth having a look at the light curves of some of these things. That's where something like ASAS is very useful. That's a bit dated now, but we now we are now getting all sorts of surveys through where you can actually look at light curves. But you've got to do a bit of pruning. You've got to concentrate on a certain kind of area, if you like. That's something for the future.
Okay.
Hey, Bert, I'm sorry, I just want to make one quick addition to the question about Pandora. It occurred to me, I just want to add, one of the other advantages of amateurs looking at target stars during Pandora, when it is looking at it, also is to help characterize the star at that point in time, if there's any flares and that sort of thing. This is one of the things we did with the that Hubble mission I mentioned earlier. Of course, all this depends on whether Pandora gets launched, given current budget considerations going on. So anyway, I just want to add that.
Very well said. Okay. I'd like to once again provide a heartfelt thank you to all of our speakers for taking time out of their busy lives to come here and talk to us today. Dennis, Mike, Kris, thank you all very much. I'd like to again thank this webinar sponsor. Voice Astro has sponsored our entire 2025 series, and we are very grateful. They provide online astronomy education, observatory resources, and research experiences to students and schools to perform observations, conduct research, and publish results. Please check out their website at voiceastro.org to learn more, especially if you are a student. I am sure that there are some good things there for you. If you enjoyed today's webinar, please consider a donation by scanning the QR code on your screen or by going to avso.org. All donations are tax deductible and enable us to offer educational opportunities like this one free of charge. And finally, as a reminder, registration is now open for next month's webinar. This one's scheduled for July 12th, 2025, to avoid the July 4th holidays. And we're expecting an interesting time with our next group of special interest leaders. You can learn more and find the registration link on our website at avso.org/webinars. I hope to see you all there. And once again, thank you all for attending. You've been a great audience, asked a lot of great questions, and we will see you all next month.